Okay, I'm back, guys. My name's Jaden Stark. I'm here to talk to you about a project that I've worked on for a couple of years now. It's another part of our Eclipse initiative, and it's called High Altitude Visual Orientation Control, HAVOC. And so the purpose of this payload is to kind of combat something that we all know happens with balloon payloads, is that they kind of spin freely. There's no real constraint on how a balloon payload spins. Of course, it's attached to a line, it's in high winds, and it's just out there in space, just floating. And so if you were going to try and stabilize a payload package, there's a couple of options. There's passive methods. You could put swivel joints to try and reduce the spin. You use swivel joints on many payloads. You could try and make your payload more passively stable by reducing the surface area that winds can act on it, so you can get more cylindrical designs, more streamlined designs. And then there are active methods. So if I want to try and guarantee a sensor azimuth position, well, I have maybe control surfaces, or maybe I try propellers, or you do all kinds of wacky, crazy engineering options. But most of those rely on atmosphere. Control surfaces rely on atmosphere. Propellers rely on atmosphere. But if you're operating with a high altitude balloon payload, you're getting really, really high where there isn't much atmosphere. And so here at the University of Alabama, Huntsville, we're an aerospace school. And so we kind of thought about an aerospace solution to this. And that would be a thruster system. Spacecraft use thrusters. Reaction control thrusters have been a part of manned space flight for a long time. And attitude control via thrust can be done in a vacuum. So we thought a high altitude balloon payload could be a platform to utilize some sort of air thruster system. And so what we've created is this. This is our second HAVOC payload, and it utilizes a compressed air source and a series of thrusters to control its azimuth orientation. So that's its, I guess, across the ground, north, east, southwest orientation in free space during the balloon flight at high altitudes. So I have a couple of slides, but we're going to demonstrate it. That's the main purpose. And so what you see here is the internal view of the payload. If I go through my slides, this is the external view. This is the CAD. We have a composite fiberglass body that we mount over this. It shields it from the wind and keeps it from the environment when it lands and just houses it. And we have, of course, the ability to attach additional hardware on the bottom. So we have attached separate cameras and sensors that are housed underneath of a clear transparent belt. So the basic components are here. So what you see is what you get. We've got a 4,000 PSI tank. It's a 50 cubic inch tank approximately. Delivers 4,000 PSI compressed air. So that's an air nitrogen mix. That's not liquid CO2. And it's just normal air. We have an adjustable pressure regulator that feeds into two solenoid valves. Those solenoid valves feed either a clockwise or a counterclockwise thruster set. So they're paired. They create a couple moment. And of course, they produce torque because we place them on these lever arms. This is a 1 meter carbon fiber wing spar that we place our 3D printed nozzles on. And so we can adjust the pressure output, which affects the torque output. And we can measure the rotation of the payload internally. We have a sensor package in here, our foam insulated package. And it has a PID controller built in for it to control its rotation. And it's all programmable. It's all adjustable. And it's fairly accurate and fairly strong. You'd be surprised that this system operates at, from a 4,000 PSI tank, we have it probably operating at a system pressure of about 10 PSIG. So that's 10 above atmosphere. Because at altitude, the thruster efficiency goes way up. That pressure delta across that nozzle goes way up. And so the thrust output at altitude, while other methods, control surfaces, propellers become less effective, the thrusters become overly effective. In fact, it becomes such of a bad response. We got, of course, instabilities with your tuning. So that's one thing we've encountered from low to high altitude is that the thruster's impulse becomes so high that the minimum impulse can become overwhelming and you get oscillations. So what you'll see now is kind of an underdamped sea level operation. So I have it tuned to operate fairly efficiently at sea level, but we would of course have a lower operational pressure. We were targeting, say, a 20-kilometer flight to turn on and start attitude control. So I guess that's the slides for the overview. So I will do a demonstration. I'm gonna use this box because I need to calibrate the IMU, which stands for inertial measuring unit. So there's a sensor in here. It's a fusion of a 3-axis accelerometer, 3-axis gyroscope, and a magnetometer. And it uses that to calculate absolute orientation in 3 axes. So in free space, it understands, based on a starting calibration, where it is angle-wise in 3 axes. And so I need to turn it on, and it's going to get its bearings. And I'm going to keep it a little still for that. It's a little unstable because it's not inside of its fiberglass shell. It's really kind of an exoskeleton that holds it together. So it's going to turn on and it tests the thrusters. I test for airflow to make sure there's no clogs and both sets of nozzles are functioning. So you'll hear that first. Then it will calibrate, and then it will get its calibration. So now it's 0 facing in this direction. And so I'm going to offset it, and it should return to that position after a time delay.
Wow. That is cool.
And so, yeah, it has a controller where it's tuned to not over respond. It doesn't force itself. It notices it's heading in the direction it wants to, so it doesn't just blast on the thrusters. But it could oppose a constant resistance if it were coming into winds. And it currently has a tolerance of plus or minus 10 degrees, so there is kind of a cutoff band. It can't get down to 0. No controller does that. So yeah, as it kind of leans and gets to the edge of its window, it makes small little adjustments. So it'll actually do a 360 if it's. And so at altitude, what does this look like? So there's a couple of things you might do. Let's say you want to overcome velocity. Maybe you're not targeting a plus or minus 10 degree azimuth. Maybe you just want to have a sensor package that spins less than 40 degrees per second, so to speak, some arbitrary value. Well, we've done that. So this is the ascending flight. This is the descending flight. And so we set a target of plus or minus 40 degrees per second. And you can see the orange data is when we turn on at about 15 kilometers. And then boom, you were locked in. Plus or minus that degree per second rotation velocity range. And then at burst, you see burst happens. But even on the descent, we're not exceeding our threshold very often. We're staying in. It's very chopped off there, right at activation. You can see the data points where it's outside of and how quickly it gets within that margin. So, I mean, this stabilization time, this is altitude, but it is about an hour and a half worth of stabilization we have with an air supply. So it is working, but it lasts not for an insignificant amount of time. It lasts for a good duration of the balloon flight. So yeah, in this instance, we were actually targeting the peak of the jet. This was flown, this was 2 years ago in about April. And so, yeah, we activated it probably the most turbulent time we could. And we very clearly could have some sort of control authority over the rotation of this package. But that's just rate of rotation. That's velocity. What does azimuth control look like? So we flew 2 flights. We flew a flight with no azimuth control. And this is what it looks like with azimuth. So this is plus or minus 180 degrees. And this is what a normal sensor would look like. It just rotates. If you were trying to plot it, it looks like garbage. But as soon as you activate and you get a little out of the jet kind of bullied us this day. Here we are locked in a plus or minus 10 degree bearing where we are holding our position in space dead set. And again, the difference between payload A and payload B is apparent. There's some sort of control authority being shown here. So this is all the demo slides I had, but I wanted to share a little bit more because we are the Space Hardware Club.
And Jaden, those flights was that the same day, same payload?
Those were the same day identical payloads. So that's not just 2 flights, that's 2 flights on the same days with identical payloads. One just was turned off as a control. One was turned on and had active control. So I can go to our website, which I guess Todd should really share this website. It has information about most of the stuff we talk about. So I can go to the HAVOC page. Oh, and yeah, here's some pictures from camera systems and stuff we put on HAVOC. Here's HAVOC in the jet. It's kind of a screaming. It's kind of on its side there. Yeah, here's our team all together. Early CAD, early renders of the payloads. Different missions we've been on. So I can go to our flight history page. Very early on, we experimented with CO2 cartridges. So if you have a little CO2, 18-gram cartridges, that's kind of where you kind of start early on. What we realized is that one, there's not a lot of propellant in there. And two, they're very sensitive to temperature. So that liquid might want to not become a gas very quickly in certain conditions. So, but what we did get was a little bit of success for a rate of rotations. This is plus or minus 100 degrees per second. And this first little box flight, which was built in under 2 months by a team of freshmen, showed some sort of target. Because that I was a freshman. Here's me. Yeah, I'm pressure testing my flight controller in here. We're testing its state machine, so we're simulating vacuum to achieve an altitude with our barometer. And so that's actually a test. That's 2019. Here's our launch day. A little tiny sensor package with a Raspberry Pi camera on the outside. So that's a very, very, very early flight. There's a video from that, but that's not as important. But later on, we develop a much more matured payload, which shows the data that you previously saw, where we actually achieve much longer duration of velocity control. So it's hours to 10 minutes of and 52 seconds of stabilization. And of course, when we found this, we were in Georgia when we recovered this, and it was in a tree. We find it, and it's stabilizing in the tree. It's up there, and that thing, I mean, we found that. It was a watch and was there. And of course, we had to call out somebody to climb and get it down.
Mr. Shane came out and got it.
So Shane recovered, yeah. So if you're familiar with Mr. Shane, the tree climbing man, he recovered the first HAVOC, and that was very very lucky for us. There's probably a picture of it out on that. There it is.
Whoa.
Oh.
The 2-month flight landed in a Google data center.
Oh yeah, so this one's also was kind of a recovery horror story. This landed in what was soon to be a Google data center. And if you're not aware, Google data centers are very highly protected. And so a contractor was building it and it landed out there. You know, you're like, can I go get my thing? The contractor's like, oh, I don't know if I can do that. And Chris, you worked on that. It flew in October. We got it back in like March.
Yeah.
And we got the data from it. So this data was recovered in March from a flight in October, and it was out in the elements. And we were already designing this new system based on the assumption that it was even possible to have a cold gas thruster payload do anything. And then we got it, and it was pretty exciting to get it back. You'd almost forgotten about it.
Did they send it to China so they could reverse engineer it?
I wonder, but based on how you guys found it, it was underwater and soaked and stuff.
Wow, that's a long period of time.
It was. And so what was recovered though was the data. Because those SD cards, when they're mated, those contacts can stay pretty clean even in a harsh environment. You take that off and you can get the data off.
Where do you get a bottle that's rated for 4,000?
That's what I was wondering.
These are consumer grade paintball tanks for paintball guns. So that is, you go right now, this is about, I mean, they're kind of pricey, they're kind of high end for the hobby. But these are completely consumer. They're meant for 13-year-olds to use. Honestly, it's, you know, DOT rated, blah, 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 certified, hydro certified. We don't have to do that. In fact, there's many people out here who will build these tanks. Of course, filling to 4,000 PSI is not insignificant. I can't hook it up to shop air. Can't hook it up to a shop compressor. So you do have to fill it from bulk containers. But that is a big thing. We were doing trade studies really early on, like what is a portable lightweight gas source? And it turns out there's a whole market. I'm trying to pull up on Google. A whole market of this type of hardware, and it's meant for hobbyist paintballs. So if I look up HPA paintball tank, which HPA stands for high pressure air instead of CO2, there are paintball tanks. They look like this. And they're carbon fiber overwrapped, so they use less aluminum, and they end up being lighter than the pure aluminum tanks. So we went towards these carbon fiber tanks. And yeah, here's a 68 4500 rated one, $180. They're refillable, reusable, very robust.
So maybe go to scuba shop and refill them?
You can, I go to a paintball range in Decatur. I've given them my business and they fill it up. You can of course buy air tanks and they sell regulators to fill these. They're kind of expensive, the regulator attachments. All hobby stuff you find out, they'll price you out. But yeah, so we figured out, oh, this is pretty good because air is not as sensitive as liquid CO2. And of course you can store it in a carbon fiber container like this, not just a pure rugged aluminum container. So it ended up being, I think, the best option for what we were trying to do.
Did you ever have any humidity coming out of the bottle, icing up at the nozzles?
No, we've never seen that. So it's been pretty dry, the air we've gotten coming out of it. So I've looked for that in video and I've never seen any sort of particulate, any sort of boost. So like I can show a video actually.
You might just blast through it.
Well, it's because it's on the outside as well.
Right.
Typically, all moisture condenses on inside of payloads because it's not exposed to elements. It's so dry in the stratosphere. So dry.
So this video is not from an attitude control flight. It's a rate of rotation control. We started kind of simple, you know, you got to work your way up. So velocity control is much easier than orientation control. And so, yeah, you're allowed to freely rotate, but don't exceed the rate. And so this is an example at a high altitude. So, and so it's rotating, but it will stop itself. Hear the thrust. It's like, boom, I just exceeded.
A lot better than the one that just lines.
Yep.
You're sick when you watch it.
It's just a little boom, but that one little boost just stops it. You know, it's very effective at that altitude. And then, of course, what's actually interesting is that when it bursts, stabilization is still turned on. What happens when it bursts? It's just fine, and it's like a spacecraft. It's making those little tiny thruster bursts, these little torques that it's moments it's creating on the descent. So yeah, it does its little thruster,
Yeah, just scrub through the video and see it. Like if you just hover over and go through it.
boom, like hear the solenoid valves. The solenoid valves have a pretty loud click to them. And those are, you know, 12-volt little valves. We bought some pretty small ones.
Back to your water concentration in the bottle. I know aviation bottles are pretty much pure down to like 0.002% water vapor because of freezing potential. So I would say you might not want to take it and get it filled on a 90% humidity day. I don't know.
I haven't thought about that much.
Well, a lot of the compressors, I'm on the fire department and I've scuba dive, they have dehydrators, so they dehumidify the air before.
I'd have to ask my supplier next time I see him.
Yeah, sure. If it was from a bulk container, it's that because you're not getting any outside air in there.
No, so you're really. I've had it pretty long.
What is the weight of this with its exoskeleton?
With its exoskeleton, it's close to 6 pounds.
6 pounds. Okay.
It's close, and it's, you know, that's your part 101 limit, and we stick to, and it's missing additional hardware on board right now, but.
Talk about the gimbal.
So yeah, we can talk about what we want to do with this, and I don't have it here, but I have it labeled down here is gimbal attachment plane. So consumer gimbals, so now drones have become a big thing, and they all have camera gimbals on them, multi-axis, 2-axis, 3-axis camera gimbals on them. And you want to put this on a balloon payload, but I can't just put it on a styrofoam box and send it, and it worked perfectly. One, because usually there's not continuous rotation along one axis. It's usually up to so many revolutions, and then you can hit a limit. A lot of software we've seen, or a lot of IMUs and stuff we've tried to use, the gimbals, Cox gimbals, hit a wall if I just spin it. Or too quickly. Their maximum controllable rate of rotation might be 60 degrees per second, 90 degrees per second, and we exceed that in the jet. So I could shake a gimbal like this and it's not perfect. But with something like this, we're now like, okay, so we're maintaining a controllable rate of rotation. We're maintaining an azimuth within plus or minus 10 degrees. If you slap a multi-axis gimbal on it, it takes up the slack. It's like, now I've got my roll and my pitch. And as long as, that's okay, which, we're not stabilizing that. It's mainly the yaw question because balloon payloads tend to rotate around this axis. If the axis they're suspended on, this is the axis they rotate. They don't do flips like this, except when they burst with altitude. Yeah. We're trying to take up that slack with a 3-axis gimbal. And so we flew one test with it. It didn't go great, and it's because of the gimbal. I actually don't have that footage on here.
You should have had that.
I should have, because if you almost caught it, that's when he almost caught, but it kind of came down, he dropped it, it shattered the gimbal. So we had a nice, like, transparent acrylic dome on the bottom, and it just shattered it, crumpled the gimbal, impacted that. It was bad. That was a bad landing. It came down in an asphalt parking lot. That's not typical. We usually don't get lucky even with that. We get in trees, and I'm like, well, if it lands in a tree, it snags. That's fine. And those carbon fiber arms, they break, but that's kind of okay. We've landed in trees, and we don't want to get skewered in trees, so they end up breaking, and they kind of fold upwards, and you can kind of tug it down. It's pretty easily replaceable. You can slide a new carbon fiber wing spar in there. So we've seen that before.
Don't you purposely put failure points?
I have drilled on there before. It's also an attachment, so it like kind of centers it, but it also weakens a specific part of it to snap upwards if it gets skewered in a tree, because sometimes they are difficult to get out of trees. Here's the example where it broke. You can see it. It's kind of slumped where we got it out of the tree. And then, we've tried multiple different launches for many different events. So this is kind of an entire flight history. Up into this one, this is actually this one's pretty cool because we flew it in the evening, so it just looks pretty cool. And I think this is the azimuth control. So it's maintaining its position now. It's not just rotation, except it's outside of plus or minus 10 degrees. I think we were more liberal with it. We were more plus or minus 30 degrees. Was acceptable. So let's see if it hits its range and corrects itself. I can't remember what the range was on this one, because tuning it is hard. Because if you do it wrong, you're going to be whipping back and forth. You're slamming back and forth between your dead man. Because I could take an Allen wrench, I could crank that up. I could be like 4,000 PSI output on the nozzle. Let's go, just hook into that tank, and it takes off. I've flipped logic on it before. Imagine what that does. You invert that, and instead of correcting it takes off. It's logic is inverted. I don't think we can do that, but there's a video of that.
Where does the gas release from?
The gas is released.
Does it come out of the tank, or is it already out the arms? And
so it is here. So it goes from this adjustable regulator, and it's metered by these solenoid valves.
So it's there. It's not out at the end.
It's not at the end. So it has to travel this delta.
Okay.
So and there's there's a loss associated with filling that volume before it hits this. Try to stay there.
What happened when you tried putting it at the nozzle instead of at the?
Well, we kind of want to keep our electronics kind of internalized. So we'd have to put the valve way out. We'd have to do all of that. And also because we have two valves, but they feed opposing nozzles. So it kind of feeds off. So these two are paired together because they work in the same direction. Right. These two are paired, they work in the same direction. So they just kind of centralized it. And then
what's the operating pressure on the nozzles themselves?
So like I said, now it's like 10 PSI. So that's above atmosphere. If it were at atmosphere, you wouldn't get thrust. But at altitude, that's fairly significant because that ends up being 24.7 PSI. And then with that long of a lever arm, and the way that the moment of inertia, of course, we kind of stacked it and balanced it such that its ability to control itself, it can rotate around that axis, it's balanced. By stacking everything vertically, your axis of symmetry along that central balloon line axis is such that it really does want to move itself. It's pretty well balanced, and they're just very effective.
Any plan to put an altitude thing on it, but you mentioned now it's a lot more effective at altitude because I think I put it 5,000 feet, don't have the amount of air it's going to use.
So we've looked at, oh, here's where it's turned on. Sorry, I'm so sorry, sir. But yeah, no, I've wanted to do that. The issue is that we have open flow solenoid valves. So, to adjust that regulator, it's manually actuated. We've thought about motorizing it. We talked about adjustable nozzles. We're talking about like plug nozzles where you can change the surface area, if your nozzle outlet, that could be something. That would require a little bit of tech to meter it at the end there. And yeah, there's proportional valves, but the response times of those are not fantastic. There are some though, of course, this is an application, like there are applications where you need that. They're just more expensive and they're just a little out there.
If you could rotate your nozzles 90 degrees, you can come down and do an Elon.
That's what we're talking about landing. Oh yeah, that'd be kind of cool. Here's actually the azimuth control flight. It actually ran out of air right toward first, so you can see it maintain this azimuth. It's just locked in. There's a little bit of of it doing the motion, but we want a gimbal, to like for a drone, because drones move, they pan and they hit, and so with a gimbal.
You could target something on the ground. For instance, you could launch from a building and have the gimbal continuously look at the building as you fly off.
Yeah, because if I know my chord and I know the target chord, I can trig, I can
Like
calculate
the
it out.
market where you come down and back.
And if I want to keep that horizon level, a gimbal can maintain that roll. But as long as you maintain the azimuth, because that was the hard part, your package was thin. And what's really cool is now, we're looking at the sun right now. So the solar eclipse, this is something we want to deploy in a solar eclipse because we want to observe totality, but we want to ensure that our cameras are locked and loaded. We are looking at totality or we're looking at a spot on the ground.
That's neat.
Because you don't want to be rotated the other way. And that, yeah, you got to be on the ball. So there are 360-degree cameras and such, and those are really good. I've seen a lot of good footage where people have flown those, and of course that looks very stable. It's just the nature of those cameras. But if you're doing specialized instruments, if you're doing, outside of the visible light spectrum, I want to put some neat cameras on. You got to get either really creative or you kind of just put it down, you lock your position with some sort of stabilization, and then you collect the data or take the images that you want. So it's something that we've been working on for a little bit, and so I'm happy to share it with y'all.
How much time span can you get off the tank like that for azimuth control?
For azimuth control, so the flight here, which what happened here is we had a little bit of an issue. So we flew this in April. This is the jet, and I don't have another plot here, but the reason why this doesn't work here, so this is z-axis. So we kind of have a coordinate system going on. So if I were to talk to you about this, I would say I'm rotating about the z-axis.
Right.
And the reason in that previous data, there's a portion where it's not doing that is because if you look at the x-axis, it says 90. So it's sideways because you're in the jet and we're rocking. You're in a pendulum, you get kind of crazy winds. And so it can't really do that roll, like that sort of yaw control when it's parallel to Earth. That doesn't work out so well. So, but when it's in a vertical upwards orientation, it's great. But yeah,
like an hour and a half.
But yeah, you get like an hour because we wasted a lot of air on that flight. That's what I was trying to get to, is that we wasted a lot of air because you're just and nothing's happening. The controller's fighting it, but we're going to try and mitigate that by cool downs and other sort of like watchdog techniques that say like, hey, don't waste air. But an hour was our target. An hour is what we have now. And so now we're just trying to perfect it and fly it for the upcoming eclipse. So
We did a pointing system about 25 years ago using 2 light sensors and a plate in between, so that both sensors had to be lit, and we had a pin on the back steering it left and right. Worked great, but it was a eclipse of the sun. And so what we didn't realize, of course, because we did this in 24 hours, we said, hey, let's take a video of the eclipse in the stratosphere because it's going to be cloudy tomorrow. So we threw together a payload and it worked great until the sun went out. There was nothing for the sensor to track.
What we're going to be experimenting now, of course, I was going to say there's governing equations on where the sun will be on Earth. You can plug in your coordinates, your UTC time, and you can say where the sun's going to be. So we're going to try and build in some of those astro equations to be like, where should I be if I'm looking in the right place right now? Because if I can know my orientation, I can try and figure out where I'm supposed to look at. Sure. So that's our current goal. And then, of course, we're looking at light sensor feedback. Similarly, we've had a team that's creating kind of an eye shape with photodiodes where they kind of have this, well, it's hard to explain, but I don't have a diagram for it.
So
but
Dave, in
yes.
April of next year,
Yes,
the eclipse is going to happen.
it will happen.
And it seems like it's around noon.
Yes.
I guess
The sun's going to be pretty high up. It'll be above you.
it'd be pretty
And
high.
so I'm looking at how I want to mount my sensor package, my camera package. I thought about inverting the entire system. You could, put the camera on top. Of course, the line's in the way. You have to get kind of creative with the rigging. But because you can kind of control your position, you can maybe make it where the line does not get in the way of the camera. You can mount it such that it's always behind me. Well, the balloon's way above you, so you will maybe get it in the shot, but with my multi-axis gimbal, I can maybe look up and I can observe this event that's happening at approximately noon. That is something I've thought about, kind of a lot. So
When do you graduate?
I graduate in May.
Enjoy this while you can.
I'm trying to, so I co-op with NASA, and so I started school 2019, but I take semesters off and I work at Marshall. So I'm working this summer. I worked last spring. And so I kind of alternate going to school and working, but I will complete my degree next May.
Will this continue on even after you graduate?
I have to see if there's a team who want to continue it. We started the challenge, that original CO2 cartridge, that was a challenge to our freshman teams coming in. That's how I started in this group. Was they proposed it as, could a team of freshmen work on this? We'll give them the resources, give them 2 months. And so it's become a neat challenge because, students come in, they want to work on aerospace stuff. It's kind of a spacecraft analogous thing. I always show people these pictures. I'm like, it goes that high, right? You realize what it looks like at 100,000 feet. And they're like, no, I didn't think about that. It's like you could build a thing and it goes up there. It's not on a rocket or anything. Like, it goes up there and it does something for not an insignificant amount of time.
For manned space program.
Sure. And so we will probably continue to train people and introduce them to ballooning because they're engineers, they're aeros, they're mechanicals, they're computer science people, there's electrical engineers, they come in and they want a task. And so we will probably keep it around probably for them to play with and to train. And, you're learning about thrusters, you're learning about nozzles, you're learning about a lot of different things. Control systems you learn about, and of course, it can be really hard, but it really is, you just got to get the people with the drive and the resources. And nowadays, 3D printers are big. A lot of people programming in high school level now. So people come in with programming experience. They come in with CAD experience. And most people now, they own 3D printers. So people come in with a lot of experience with those tools to where if you just say, hey, just apply it, they do pretty well.
The students pick the projects you're going to work on?
So when they come in, we have what's called 2 months. So actually it's crazy. I can click the button. I can tell you all about it. And we usually give them a select series of mission concepts. And then they have mentors related to those mission concepts. And so in 2 months, they do a month of classes and a month of design and construction to where they complete their project and fly it. So sorry, I'll come back. So yeah, here's just some team working.
It's all student run.
Oh, it's all student run, so it's all student mentored as well.
Yeah.
So
That's amazing. You guys do some wild stuff.
So yeah, here's the balloons. Here's some laser cutting. Here's some epoxy work, software work. That's some rover work. We have a rover team, so we don't just fly stuff. CanSat. We have the international CanSat competition. Oh, there's Grease Lightning. We were talking about this. That's the glider we dropped. That's the Pizza Hut box that that crew made. There's Todd. He got our payload.
Yeah, you want to get a payload out of a tree, buy a crossbow.
Yeah, we've crossbowed payloads out of trees. It's fantastic.
Yeah, we've had to use that before.
Yeah. So that's all I have for the HAVOC system. Oh, one last thing. This is just, I promise this is the last thing. Is that check us out on BAM. So we have a paper coming out. It's in pre-release. It's in pre-release in the
it's actually go download if you look at the PDF. It's updated now.
Oh, I can do that. So yeah, we actually just published in the Bulletin of the American Meteorological Society a platform for active stabilization of high altitude balloon payloads, and so it is all here now.
So you can go read about it. It gives all the parts.
Yeah, it lists the parts.
Try to build one yourself. You can see that's the board.
There's a proto board, so you see that's our IMU. There's our microcontroller, data logger.
What's really cool about this project specifically is it has a lot of individual components, and they're all of moderate to high difficulty for like undergraduates, for example, doing it. So if you have like a team of people, it's a really cool technical challenge to build one of these. It would kind of be a lot to undertake for yourself because there's a lot of different systems you have to consider and a lot of code you have to write. So if you have a dedicated, group of students, this is a great project to do.
Yeah, it was good for me in my career and a lot of the people who came on and worked on it. So if you can see it all here. One more question, yes, sir.
See, it wasn't the next one. This is brilliant. What is, and it's well thought out, of course. Well, what are your plans, or do you have plans and funding or whatever it takes to kind of reduce it in size and mass and that type of thing? I mean, there's probably some possibility to do that.
I agree with you. And so currently that would be something I would probably look at post eclipse. My focus now is I got to get this thing in the eclipse. And so if I were going to try and reduce it, that'd be something I would have to probably think about post April of next year. But I have thought about it because you kind of, for Part 101 exemption, for example, you really got to watch your weight. So if I wanted to fly more than just this on a line, I'm really restricted. You could fly 6 pounds of additional payload, but you got to have a balloon that can carry 12 pounds at that rate. So I think there are ways to reduce it. And I'll probably, as the years go, I'll be a senior next year, but we'll have freshmen coming in. There are younger people who can maybe tackle this and give their input. And I'm wanting to give it to those younger undergraduates. And then if you start with this, they could probably bring it to a reduced version. If the predecessors came from scratch to bring it to where it is now.
You're there except for size. Yeah, you're there except for size.
I think I'm there except for size and mass. I think mass is a big thing. And of course, mass and aerospace, that's the killer. So if you were to say, here's a mass problem, fix it. There's a lot to learn there.
Good luck.
Thank you.